Thank you so much, Setma, and thank you so much, everyone. I know it's like 6 p.m. over there in Sri Lanka, so it's the afternoon. So hopefully you guys got some coffee, got some tea, and ready to get going. And maybe learn a little bit about machine learning, and I can probably instill some of the experiences that I have obtained in the past decade of working in this field. And hopefully I can, it'll be a resourceful session for all of us. So before I start off, I want to thank you, Dr. Mahanama, Dr. Damayanti, and the student coordinator, Madhushan, for putting this all together. I know we've been in the talks for a couple of months, myself and Dr. Mahanama, and I'm happy that this came to fruition today. So happy to be here, and thank you so much for taking this time off your busy schedules to attend to this this session. And yeah, all right. So let's kick off. Oops. See. Okay. Here we go. All right. So in the beginning, what I'm going to do, I'm going to actually set this talk as more like a story. And I'm going to basically introduce myself, and then I'll go over the agenda of what the next 40 to 45 minutes is going to look like. But before that, again, I want to thank you again for being here. It's a privilege for me to talk to you all. University of Peradeniya is my alma mater. I'm an alumni of the University of Peradeniya. I graduated from Pera in 2008. I did electrical engineering. So it is really a privilege for me to come here and talk to you all. So currently I reside in Boston, Massachusetts in the United States, and I am a new dad. I have a 3-month-old, and so I'm actually on paternity leave now, so that allows me to work on talks like this in my free time. But usually my real work is I work as I lead a team of data scientists, machine learning engineers at American Express. My department is mostly focused on managing fraud, e-commerce fraud and financial tech fraud mostly. And also I also work as an adjunct professor at a university called Northeastern here in Boston. At a personal level, I really enjoy learning new technologies, particularly pertaining to machine learning. And then, of course, I love spending time with my family, working out whenever I can, and I'm also lucky enough to live by the ocean, so during the summertime I really enjoy an ocean swim. So that's a little bit about myself, and what I really want to get out of this talk is for you to go home and really be excited about this field of machine learning and build cool machine learning applications. So hopefully I can inculcate some sort of encouragement where you can pick up from here and then think about building some cool applications around prediction and things that we will learn in this talk. And I want to preface by saying one thing. This talk is not going to be a very technical talk. It's going to be more like rather than going into depth, what I was thinking is maybe it'll be beneficial to have a conversation around the breadth of opportunities and applications around machine learning, so that you can choose whichever area of focus that you want to learn in, and which I thought would be beneficial rather than going into a much more deep dive conversation on a technical subject. So yeah, all right. So let's kick it off. All right. So the agenda for today. In the beginning, I'm going to talk about a little bit of the motivation behind artificial intelligence / machine learning, what they are in a nutshell, and then I'll talk about some of the applications of AI, and maybe how machine learning differentiates, how are the certain how do I say it? Certain algorithms in machine learning, what's them from each other, maybe in a very generic way, so that it's easier for you to learn and it's easier for you to remember. And then I'll jump into fraud management side, which is my bread and butter, which I've been working in the past few years, so I can talk about that. And then I'm gonna do a little bit of context switching and then talking about like how to build this leadership muscle. So like hopefully you can, this will allow you to get more excited about this field and you know, start working on these projects. So on, you know, as graduates, you're in a really good, I would say, really good time in your life where you can like be excited about starting a new company, new startup, or new application. So, you know, so yeah. All right. Okay, and then I leave 10 to 15 minutes. If you have any questions, feel free to direct at me, and hopefully we can cover all that. All right. Okay, so motivation for AI and machine learning. So I'm sure most of you have heard about artificial intelligence by now, what it means, and at least in a generic level. So I'm not going to really go deep into it. What it really means is we have a, let's say, a hardware element or a software element trying to act as a human, at an human level intelligence, right? So we assign this hardware or this software element like a certain task, a certain policy, and a certain reward system, so that the agent, the AI agent, so to say, will learn the optimum path to get to this goal, right? So an artificial agent is more like it's if you think about it. So I'm going to actually give you an example, which will make it easier for you to comprehend like what that means in a more generic level, and then there's another term that I'm sure you've heard of, which is machine learning. And people say it's a subset of AI. I don't really know. But what machine learning really is like, it's, for me, it's really like encoding the past to predict the future. And really like parameterizing like past phenomenons so that you can predict what the future is going to look like. So it could be a subset of AI because AI is more like I would say more like an organic live learning kind of a way of thinking, but machine learning is more like I would say like a static way of learning. All right. So let's jump into an example. All right. So I was thinking about like what would be a good example to talk about AI, and you know, I just came up with this idea. I was like, okay, I love coffee. So what if I want to build my own coffee shop? Okay, so let's say I'm this entrepreneur and I'm like, I love coffee. I want to build my own coffee shop. How am I going to start? So what I'm going to do is I have a friend in South America. Let's say I have a friend in Nicaragua or something. And I talk to my friend, and my friend is like, okay, I have coffee beans, so I can send you coffee beans for your coffee shop. I'm like, oh, awesome, I'm excited. So my friend agrees to send me coffee beans, but my job is to, let's say, segregate good coffee beans and bad coffee beans, and then start the process of roasting it, and then, you know, building my coffee shop. But the first task is to once I get the coffee beans, I want to segregate the good versus the bad. Okay, so this is an arduous process if I'm a human being trying to do this, right? It's like really hard. So I'm thinking, all right, I'm an engineer, so I'm going to build like a robot to do this. I'm going to be like thinking about like maybe I can have like an AI agent differentiates between the good coffees and the bad coffees. So how can I build this system? The easiest way to think about this is to put this into a framework called a PEACE framework. P stands for performance metric, environment, actuator, and a sensor. So the performance metric, it really comes down to sort of a, it's really like assessing the performance of your AI agent, right? So let's say I built this conveyor belt, and there's a conveyor belt where the coffee beans are being passed, and the sensors are like a camera or a weight scale, and then actuator, which is the action, is some sort of like a robot arm saying that this coffee bean is a good coffee bean, this coffee bean is a bad coffee bean. So we can build a system like this where the performance metric could be once we run this program one time, we have a bucket of good coffee beans and a bucket of bad coffee beans. And this was decided by the AI agent. Now the performance metric could be, we look at the good coffee beans and we can say like, okay, of the good coffee beans that the robot predicted to be good, how many were actually good. So that's one performance metric. And then we can say of the bad bucket, of the bad coffee beans, the robot said those are bad, how many are actually bad. So we can set up some performance metrics around that, right? So we have the performance metric. This system really doesn't engage in the environment in more like a feedback loopy way. So I wouldn't say it's more like a static learning AI agent. There are other AI agents that actually like interact with the environment, like Roomba. I don't know if you guys heard of it. It's a vacuum cleaner thing. It goes around your house and pick up dirt. And we can set up policies, reward systems to build that AI robot. But it actually actively interacts with the environment, learns the constructions around the room. Um, but in our example, this conveyor belt is much more static. So I would say it's a static environment as opposed to a stochastic environment. And then the robot arm is the actuator, and then we have the sensors, which is the camera, the weight scale, and all that. So we kind of came up with this idea, right? We have a use case, and we put this framework into place. So we came up with this AI robot. Now what we have to do is we need to like kind of train the model, which I get into in a couple of slides, train the model and then apply these performance metrics to see if our algorithm works good or not. Right? Okay, so that's AI, that's kind of like on AI agents, but I want to kind of emphasize on a couple of things here. When we talk about AI agents, there's this one component that comes into play, which is called the states and observability. What this means is when we build let's say an AI agent or an algorithm, what you need to realize is there's something called the context, right? So it's this interesting phenomenon, like where when I'm like actually talking, what you hear are words coming out of my mouth. What you're really interested in is the context that I'm trying to convey, right? So the same thing, right? When you look at my face, you can see my facial expressions, but you're really interested in is that hidden state, the state of what is this mood, right? Similarly, like let's say the stock market, you see the stock prices going up and down, but what you're really interested in is if it's a bear market or if it's a bull market, right? So the environment that you're interested in could be slightly different from the actual observations you make. So this brings into algorithms such as like this you can think about like probabilities. I can think about hidden Markov chains. So this you can expand on this idea quite a lot. So I don't know if you're doing courses on this, but yeah, if you're interested in, there's a bunch of like searching algorithms like A*, uniform search, and all that, which pertains into this topic. If you want to have like a foundational understanding of how an AI agent works. But I'm not going to spend a lot of time in here because I want to move on to this other part called machine learning. So I hope there are some questions at the end. So I'm not going to pause. Do you have any burning topic to ask? Okay, so jumping into machine learning. So when I think about machine learning, I really think about my undergraduate time. We learned a lot of equations, right? I don't know if you guys do still, but I remember learning all these equations, and I remember like learning these constants. After doing like back and forth a lot of trial and error experiments, people have come up with these constants, these parameters. But over the course of the last, I would say like the last 10 to 20 years, what people have discovered is why do we actually try to do all these experiments and come up with these theories? Why can't we have like some sort of an algorithm where we input the data and we can look at the output of the data and let the algorithm figure out what these coefficients, weights, and parameters are. So machine learning is really that. It's really parameterizing the relationship between the inputs and the outputs of a function. And the way we achieve this is by solving an optimization function. So let's go back to our coffee shop example. So let's say now that I have my coffee beans all set up and I have really good coffee, and people start coming into my coffee shop. Okay. So in the morning hours, I see a lot of people. There's a lot of traffic coming in. There's a lot of foot traffic coming through my coffee shop door, and people are like so excited to get my coffee in the morning hours, like from like 7 a.m. to like 10 a.m. And then it kind of dwindles down from there. And then it picks up again around like 3 p.m. when people want like a refresher or something. But usually it has like a couple of peaks throughout the day. And as the owner of the coffee shop, I'm thinking, well, do I really need to hire like a cashier and a barista and these all these workers in my coffee shop throughout the entirety of the day, or should I just hire these people in the morning hours and then in the evening hours? So that's a business question that I want to answer, right? So how do we mathematically or statistically get to that point? So how do we really understand what that time frame is? One of the easier way to understand this is to put this into a time series problem and understand the nuances where, or, what that traffic looks like throughout the day, and then I can predict what the traffic is going to be in the future on a given weekday. Let's say on a Monday, most people come to work, therefore the traffic is like way high compared to, let's say, on a Thursday, where people may be working, maybe more reluctant to come to work. They probably prefer to stay home and work, so therefore the traffic goes down. So how can I understand this, like all these like complexities, right? So I can put this into a machine learning model, a time series model, where I have seen people coming and getting coffee. So I can get a data set because people would come in and they would use their credit card, they would swipe their credit card. So I can get a data set and have the timestamp when they came in, and I have the transaction amount that they've made. So I can put these together and possibly build a data set. So let's say like my data set is going to look like I have a context window. So I would say, okay, for the last 3 hours, how many people came in? Last 6 hours, how many people came in? Last 9 hours, how many people came in? Likewise. So I have like this context window that goes back like every 3 hours or so, and I can create this data set, which will be my X, which will be my input data set, and my output data set is the number of people inside the coffee shop. So now that you have this historical data set, you can run this through some sort of a machine learning algorithm, and you can try to understand the relationship between inputs and outputs. And what you're really training, or what you're really trying to understand, is that the coefficients or the weights that actually connects those two together and creates that function f(x) equal to y. Okay, but what we're really interested in is, given x, how do we predict y? So the probability of y given x. That's really what you're interested in. And to get to that point, there's a bunch of algorithms out there. The easier way to comprehend this, in my opinion, is to understand the underlying cost function that's being solved. So if you have let's say, a numerical problem that you're trying to solve, just like the amount of people who are actually in the coffee shop, which is a numerical value, you would opt for I would say, a cost function. You're trying to solve a cost function like a sum of squared errors. Sum of squared errors is essentially the predicted number of people, like you can say the actual number of people inside the coffee shop minus the predicted number of people in the coffee shop predicted by the model, and then you square it and then you add them together. So that'll be the sum of squared errors, and then you take the root mean of that, and then that would be a convex curve that you can find the global minimum on, which will give you the optimum parameters, optimum weights for that particular algorithm. So that's like one way of approaching that problem, and we call that regression. So regression means you're solving a numerical problem. Let's say there's a different problem you want to solve, which is like, let's say my problem is more like, I want to understand what are like what are like the good patrons that comes into my coffee shop. Who are the people who loves coming into my coffee shop, good business because they bring their dog, they bring their kids, so they always buy more than one coffee. So I want to create this loyalty program to them, whereas some other people who just, who are just passing by my coffee shop and they would just come to the coffee shop. So I want to create this binary variable distinguishing between really good customers versus like regular customers. So that's more like that's not a numerical problem that you're trying to predict. That's more like a classification problem, right? So it's a binary outcome. You have a binary variable that you're trying to predict between the two. So in that case, maybe root mean squared error cost function might not be the best cost function because it might not give you a really nice convex curve for you to optimize. So in that case, you would opt for a more like a cross entropy or a log loss kind of a function. So based on those cost functions, you can kind of typify what sort of machine learning algorithm you're going to be doing. What is the use case that you're solving? So it can be a classification problem, or it can be a regression problem. There's a bunch of like algorithms out there for you to perform. So I would say, if it's a more like a columnar data set, a historical data set, and your problem is a supervised learning problem. Supervised learning is you have the input data and then you have the output data, could be like a target or label. I would say boosting machine models are the best. I would say the best models. I mean, the others have their benefits as well, but in my experience, boosting machines perform really well. Or you can like stack them together and do all kinds of like cool stuff. All right, so that's on supervised learning. So let's move on to this another concept called unsupervised learning, which is like mostly what the use cases are going to be like. Because in your everyday life, getting that y variable or getting that label or the output variable is not going to be easy. But you'll probably be able to get a bunch of data. So unsupervised learning is where you actually don't really have like a target. You don't really understand what this means, but you have a data set. So, excuse me. In that, what you can do is, now that since you have a data set, what you can do is you can actually try to cluster these samples, so these data points, based on how similar they are with each other. And the similarity is based on some kind of a distance metric. And these distances could be Euclidean distance, can be like Manhattan distance, Hamming distance. Like for particular use cases, you can actually have particular or different different distance metrics. So, for example, like if you have like a location problem, like a searching problem, going from what is the best way to go from point A to point B, you might be using more like I would say a Manhattan distance metric as opposed to a Euclidean distance. Similarly, like if you want to do like string matching or like figure out the distances between two strings, you would probably try to go for like a cosine similarity, or you would use Hamming distances, something like that. So those are a couple of like use cases that you'll probably run into. And then there's another algorithm, or I guess conceptually another way of modeling a machine learning problem called reinforcement learning. So this is where like we penalize or reward when the model gets the answer correct or wrong. And reinforcement learning, I think like one of the really great examples for this is ChatGPT. They did reinforcement learning with human feedback. Yeah, so that's really it. And so that's really it on machine learning. So let's just talk about some kind of like, I think we kind of discussed this, but I want to go over some of the things that you can also start thinking about, and then maybe we'll go into talking about some use cases after this slide. Okay, so we discussed supervised learning, and then semi-supervised learning is where like you don't really have a lot of labels that are labeled data. You have a few labeled data, but you want to use this as the gold standard, and then you have a lot of unlabeled data. Few shot learning or zero shot learning are examples for this. one of the good examples are facial recognition. Like, it's probably hard to get a lot of faces as a data set. So rather than really understanding the distribution of the face, maybe it's easier to understand the distribution of the similarity matrix between your face and a different person's face. So like you can create like a more like an autocorrelation matrix. Like you have your own face, and then you have you can find the similarity, dissimilarity essentially between your face and another person's face, and then between your face and your face again. And then that's called like few shot learning, where you're trying to understand the difference matrix as opposed to understand the really like the distribution of that of your face particularly. Zero shot learning is similar, I would say, but it's that kind of that's more like around something called pre-trained models. So here I have mentioned transfer learning. Again, transfer learning is where you so let's take an example. Let's say what would be an example? Let's say, all right, let's go into a coffee shop example. All right. So we are doing great on our coffee shop, and we are getting some Google reviews on our coffee shop. So and Google reviews go from 0, I think 1 to 5, right? Rank between 1 to 5. So we have some textual data, some people writing reviews on our coffee shop, and then we get the star, how many stars we got, like between 1 and 5. So now I want to build a model. So let's say to see like when I input a review, I want to kind of get an output like what is the rank for this review. So that's like my use case. So it's more like a natural language processing problem, where again, like going into understanding that hidden state where I input the text data, but what I'm really interested in is the sentiment behind that data, the text data, right? So in order for me to build this model, it's going to be so difficult for me to learn the language itself, right? So it's written in English. So before even understanding the sentiment, you need to understand the language in itself, like how the grammar works. It's a phonetic language. Like how does it work? So that's going to take so much more data, so much more like compute power to train a model. So rather than like going through that, you can actually like get the use of a pre-trained model that Google has created. Called, let's say we use like a generic pre-trained model like bidirectional encoder representation of transformers for T5. We train model that understands the language of English. Then we can append the data set, the review data set of it, so that we can understand the sentiment behind the reviews. And then we can train this entire so that now you have a new model, a fine-tuned model, so to say, which understands the English sentiment pertaining to your coffee shop reviews. So now you have a model where you put in some reviews, and you can understand, you can classify between 1 to 5 whether this review is a 5-star review or a 1-star review, and then you can understand even the sentiment behind it. So that's transfer learning. And then I want to talk about something called edge machine learning. Edge machine learning is an attempt by several companies. I would say this was started by Google. I would say, I don't know, maybe like 5 years ago or 10 years ago, when all these privacy concerns started to emerge. What Google tried to do is they were like, well, the biggest problem in terms of data privacy is the fact that the data leaves the device, right? So if my data leaves my device and go to a server, and the server computes the server does the inferencing and produce a probability back, the data actually leaves my device. So that's where the privacy concern starts to happen. So why do we let that happen? Why don't we put the model in the device itself? So this concept kind of inspired them to think about being able to put these machine learning models in the devices itself. So if you're interested in, you can learn about CoML. I think it's an Apple. I've actually never worked on CoML, but I've done some TF Lite, TensorFlow Lite applications in the past, where what you're really trying to do is you want to deploy the model in the device itself, so that the data is secured with a sandbox inside the device, and then what leaves outside of the device would be the probability, or maybe like a quasi probability or quasi data that's not really PII, personally identifiable information, but it's more like a quasi, more like an encrypted kind of a data payload that leaves the device, goes to the server, and then do the computation, right? So that's also another approach of doing machine learning. So like we talked about supervised learning, unsupervised learning, transfer learning. There's a lot of like use cases out there. And there's a lot of like plethora of algorithms that you can use to like really solve like different use cases. And I'm going to spend a couple more minutes on the other two types as well. A/B testing, it's really not a machine learning model, but it comes into play when you deploy a machine learning model in production. So again, let's go back to our coffee shop example. So let's say I'm doing really well, and I started my coffee shop. I'm doing like really well. So I'm like, all right. Usually I do like traffic, like when people just come in, they buy the coffee. But now I want to create a website where I'm creating a website, and I want to make sure that people can order the coffee through the website, and they can just come and pick up the coffee. So that like kind of alleviates that foot traffic that comes in through the door. But I can just open up this other window where the people can just come up and just pick up their coffee and just leave. So that is good business for me, and I just have to put up a website. But before I do all that, I want to kind of understand, like, is this really like worthwhile for me to do it, right? So what I can do is I can like sort of do like some kind of an A/B testing. A/B testing is where you have a control and a test. So basically, what you're trying to achieve here is, what you're trying to look for is, I guess there's like two approaches of doing this. There's one approach called the frequentist approach. The other approach is called the Bayesian approach. The frequentist approach is, I'm sure you heard about p-values. That approach really is telling that you're differentiating between two hypotheses. There's a null hypothesis, and you're trying to break the null hypothesis to say like your website is doing statistically significantly doing better than not having the website. And then the Bayesian approach is like more like you're actually dealing with like beta distributions, probability distribution of probabilities, and then taking samples of that, and then using conditional probability to understand the same kind of idea. I personally like the Bayesian approach because it's easier for me to convey the message to my leadership when I do A/B testing, as opposed to saying to someone like, okay, the p-value is so and so, and therefore it's statistically significant, which goes over the head of like a lot of like people, right? So it's easier to probably say there's a X amount of probability better than not having a website, rather than saying there's 0.005 p-value, right? So anyway, so that's around A/B testing. There's another way of doing it. It's called multi-arm bandit. I'll let you like Google that and learn about that as well. And then another type of application of machine learning is building recommendation models. So I'm sure you watch Netflix and Spotify and things like that. They're all based on recommendation models. You can learn about I think you can start with collaborative filtering, and then you can expand your knowledge on that as well. All right, I feel like I spent a lot of time on this slide, so let's move on to the next slide. I'll spend a little time on this slide. In the interest of time, let's do a time check. All right, okay. So so applications of AI. So like I said, classification, remember cross entropy, log loss, so that's the cost function you're trying to optimize. The use cases would be, classic binary variables. You're trying to distinguish between whether it's fraud or not fraud. You can say different classes like weather prediction, or something interesting like passing a gene expression to differentiate between cancer cells versus non-normal cells. So those are examples of classification models. Regression could be a continuous variable that you're trying to predict, so stock or sales price predictions could be good examples for that. And then comes natural language processing. This is like this is getting a lot of heat these days, which I think is amazing. So like chatbots, I'm sure you've used GPT, ChatGPT, and all of the other cool language models out there. Machine translation, translating one language to another. And then CV, computer vision problems like stable diffusion, image segmentation, denoising, object detection. Those are like certain use cases that you can also learn around these particular umbrella topics. All right. Okay, so I'm now going to switch to talking about like the field of fraud management that I'm actually in. But I'll try to spend not a lot of time on here. Applications fraud management. So fraud is an interesting problem to solve because it's a moving target. Unlike other I would say other use cases where you're interacting with the environment and the environment doesn't really change that much. Like let's say you're building like an autonomous like vehicle or something. The roads or the traffic, once you really get an understanding about the distribution of different random variables, it doesn't really change that much. But in fraud, the random variable is a human, right? They're always changing the way they're attacking the website or your device. So it's a moving target. So which poses an interesting problem where the idea of the machine learning problem is to be able to generalize past data, generate or encode past data in a more generalized sense. So the precision is low, but the recall is high. So I'll explain what precision and recall is in a minute. But what I'm trying to say is when let's say like a fraudster figures out a backdoor into a website, and they're like, all right, I'm gonna do a distributed denial of service attack using this set of IPs, and they're starting to attack, right? They're starting to attack this website, and then the company figures out, all right, we're getting hit by this set of IP addresses, but I can't have my machine learning model to quickly like learn about these IP addresses and like give a high probability. It's gonna take days. It's gonna take like weeks for it to figure it out and go through that, train the model and being deployed, the model being deployed, to go through all the unit tests and all that. So it's too cumbersome and it's never gonna work. So what we have to circumvent that is we have this deterministic rules in place, and the rules, you know what rules are. Rules are like if the transaction comes from this IP address and it has this payload, blah 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 blah, you can have this like rule written, and if it passes that rule, we can reject that transaction, right? So it's this hybrid model where you have rules, and then you also have a machine learning model, and the machine learning model produces a probability output. And probability is an interesting thing because it's not really telling us whether it's a fraudulent transaction or not. It really for us to kind of think about like, okay, how do we set the threshold, right? So fraud is an interesting problem. It's a hybrid model between deterministic rules and a generalized machine learning model put together. And so creating that platform is a little tricky because you're like always like kind of fine tuning the model and to like go along these static rules, and it can be an interesting challenge. But I'm going to jump into this confusion matrix right here to kind of like show you like how we assess how we really set that threshold to say that, okay, above this threshold we're going to say it's a fraudulent transaction. Below that threshold is going to be we can just say it falls into a review bucket where the transaction is being reviewed by a human, or actually we can allow or accept that transaction. So as you can see in this confusion matrix, what we do is we build something called in a very rudimentary way, I would say, we built a precision recall curve. So what is recall? Recall is true positive rate, so which is of all of your actual fraud, how much correct how much fraud did we correctly predict, right? That's recall, true positive rate. Precision is the other way around. Of all of the fraud that you predicted to be fraud, how many did you get right? Okay, so those are like two different ways of looking at the problem, and you have to find that fine balance between the two. So we can draw a precision recall curve, and we can find the threshold. We can by like kind of computing that we can find the best threshold to get the best of both worlds. No, but that's like a very simplistic way of explaining that. It's way more complicated than that, because anyway, I'm not gonna get into it, but it's a very simplistic way of explaining like how we do the performance assessment on these models. All right. So then moving on, I'll give you a little bit of like a kind of like an overview of like what I have done in the past, I would say 5 to 6 years or so. My main contributions at my work was to understand the data really collected from devices. When I talk about devices, it's like it's your mobile phone or it's your browser that you go into websites. So like if it's a browser, it could be Chrome browser, it can be Safari. So you use those browsers to go into let's say an e-commerce website. Let's say you go into Amazon.com, you go into a financial bank, or go into sampadbank.com, whatever. And whenever you go into those websites, what we do is we drop a JavaScript, and the objective is to really collect all of your information about your browser or your mobile application. Essentially, we capture like we drop elements like cookies, DOM local tags, and we collect IP address, use agents, and all kinds of information, just so that we can profile you, just so that we can understand and identify you. And then we actually drop soft elements in your browser. And even if you like, clear your cache, they're like still persistent in your browser. And then we build like other models to do something called browser fingerprinting. What that means is we want to like uniquely identify your browser, your mobile application, so that we have like this registry to know that okay, this is you. When you make a transaction using a credit card, we tie those two and multiple other elements together so that we know that for sure this is the person who is making this transaction, and therefore we can pass or fail your transaction. And I don't know if you have encountered like two-factor authentication alerts coming onto your phone, like saying is this you who made this transaction? So that's like usually when that's like really it went above the threshold and it went above the review, and then it actually went into the reject, so that's when you get that two-factor authentication on your phone. So that's really the models that we built. Again, we build models in the application itself, I mean the device itself, excuse me, and we build models up in the, like we send the data upstream, and then the server will give a probability feedback as well. Other particular use cases that I can highlight here is account takeover. Account takeover is really, rather than understanding a transaction at a more atomic level, I would say, at a more a snapshot level, we track the entire behavior of an individual across an account and across multiple accounts. So if you have a bank account, and if you have like an account on Amazon, if you have an account in a different bank, so we're able to like track you all across these like different I would say different organizations. So we kind of have like this really good like profile about you. And these are like very interesting problems, and for us to scale into building these like different unique models, for many people, it becomes a very daunting task. So, we build like, recurrent neural networks, LSTM models to like, capture that data, but there's inherent limitations in those models because, it can't go it can't go too far back to understand, what you have done in the past. So we do have to make these, I would say, computations like computations for like very large computations to say where the biggest problem really is in this field, the biggest issue is real-time inferencing. What do I mean by that? Real-time inferencing is where you get a transaction and we get like less than 50 milliseconds to give a probability feedback. So that means like we can't do a lot of pre-processing of the data. We get the data, and any pre-processing we have to do in a separate offline process, and then feed that data into supplement that data, augment the real-time data that we get, and then we can produce that to the machine learning model to get a probability feedback back. Yeah, so that's one of the biggest problems we have in this field. Anyway, I don't want to get too much into it. Let's do a time check. All right, so actually we are approaching the bottom of the hour, or the top of the hour in Sri Lanka. Okay, so just to give you a little overview, sorry for context switching, just jumping into what a data-driven solution company looks like. This is like really, in my experience, what I have encountered in the past. So other people who are in this field might have different experiences, but by and large, for me, in the beginning, what we do is we have the engineering infrastructure, the architects go in and build the data lake, a data pipeline. They figure out like the compute power, the storage capacities, and all that stuff. They build the data lake, and then comes the data scientist who builds models on a lab environment. So if you have played around with like Google Collaboratory, AWS SageMaker, Studio Lab, those are like more like Jupyter Hub environments where you can play around with and build like a prototype model. And then when you want to scale it up, maybe a machine learning engineer can help you maybe productionize your model. And then you build your model on like a let's say on a development cluster, and then a machine learning engineer could potentially help you to move that to more like a production cluster. And a data engineer really is someone who kind of helps with the parsing of the data. So the data might come in like I don't know, JSON formats, and a data engineer might try to convert that into a Parquet format so that that's easier for you to read, and they might build the pipelines also. And a data analyst is, I would say, someone who understands, who probably sit close to the product teams and then the C-level, the decision makers, because they are really like they're really like taking the layers off of the data and exposing what the context in the data to the leadership really through dashboards. So they are more like building BI dashboards. So they have a little bit of knowledge about machine learning, I would say, but mostly I would say their contribution is to build those platforms that the C-level people can go in and understand, okay, where the business is going and make those product decisions in the future. A couple of things that are also important is model lifecycle management. Which is like, now if it's a data-driven or solution-driven company, you're going to be building a bunch of models, and you got to have a track record of what the models are and what data went into the models. Because in the future, I think we would have a lot more regulations that's going to come around AI, which will be asking us questions like, okay, what were the data that you used to build these models? What assumptions did you make? Can you explain the model's decision making? Which opens up this can of worms. So model lifecycle management is also becoming an important concept to think about. Again, like I said, like machine learning operations, which is similar to DevOps. I'm sure that you've heard of DevOps if you're computer engineers, but MLOps is similar because machine learning is slightly different from having like this like for DevOps, you really know what your blueprint is when you start doing a project. But for machine learning engineers, you really don't know. It's more like an iterative process. So because you got to like do trial and error all the time, MLOps is slightly different from DevOps. And then you still do like continuous integration and continuous deployment when you try to deploy a model in production. All right, let's move on to the next slide. All right, again, context switching time. So this is really a slide that I always wanted to kind of put up for you guys, something that I try to establish in my life. And, so I don't know, this is like, I hope that this might be beneficial for you all. What I really want to instill is becoming a leader, and a leader doesn't mean that you have to have direct reports under you to become a leader. You can be your own leader where you can be better. You can be a better self of you than yesterday. So what you need is discipline. Establish discipline. Discipline is really like doing things that you don't want to do day in, day out, but you keep doing it. And you build that muscle. You build that muscle of discipline, so you always progress in your life. And then there's going to be a lot of like information that you're probably going to get bored. Like, so for example, back in the day when I was growing up, I kept hearing this notion where access to information will give you a competitive advantage. But now I feel like it's really not having the access to information. It's more like how to pass the information, or how to like curate the information to your advantage or to solve your use case. And that would give you the competitive advantage. So that means like you might get bogged down with like a ton of information, and then you probably get like exhausted by the amount of information on a particular subject. So to avoid that, I would say time box. Like whatever you want to do, just set up a timer and say like, okay, I'm going to learn about this, but I'm going to, no matter what it entails, I'm going to only spend 40 minutes on this topic, and I'm going to only open 5 tabs on my browser, and I'm going to learn that. And once it's done, that's it. I'm going to move on to the next thing, because there's going to be way too much information for you to just absorb at a given time. So I would say utilize the tools out there. Be inquisitive, be a lifelong learner, and always empower your colleagues. Try to learn to work with different stakeholders. Like just try to understand like how to work with other like peers from other universities, peers from colleagues from other cities, everybody together, and build systems and applications where you utilize everyone's like everyone's knowledge. Try, fail fast, learn and repeat. Always have a good foundation on your first. Always use first principles and get your foundation really good. Once you establish a really good, you know where you're going to fall onto. So you have really good first principles. From there, you can build up on anything, and then hopefully you can become an ambassador, and you can help your future generations and teach them how to become better, great leaders. All right, so I'm going to leave you with this slide. This is a slide I put together, the things that I'm kind of like interested in these days and looking up on. Before we conclude, I really want to kind of like challenge you where I want you guys to build an application. It could be a machine learning application, it could be a web application, whatever you guys want to build. But really what I want to like really drive or push for is this perception of like moving away from like building this more complicated algorithm or the more to building something that generates income, that brings in money, or building something that's rewarding. Because you get like you can get lost in the theoretical components of these topics, but you don't really like kind of think, how can this apply to solving a real world application? If you can solve a real world application, there's going to be demand, and the demand will get you the funding. So you always have to think from top down, where you think about a business or a real world application that you're going to solve, and then you figure out, okay, what is that algorithm that's going to take me there? And it could be the simplest model. I would say the simplest model is the best model. if you have an idea, create a proof of concept. There's a minimum viable product document that I've linked up here. You can read about that. It's about like how to get customers, how to keep customers. And then a tool set that you can use is Google Collab environment. I don't know, maybe you guys are using this already. AWS SageMaker has a free Jupyter Hub environment, and then PyTorch. I would encourage you to learn about PyTorch. Hugging Face has a lot of like cool pre-trained models, and there's a notebook section as well that you can learn from. The hip, I guess, the machine learning models out there today is the large language models. So learn about large language models, GPT, Auto GPT. You can learn about how to deploy model. Any doesn't matter the greatest model that you create, if it's not going into production and is being decisioned on or being inferenced on, your model doesn't mean anything. So if you can have the greatest model, but if it's actually not doing anything, it's not in production making decisions, I mean, it's not useful. And then think about a business proposal, and always think about how can you monetize your problems, and then yeah, you can pretty much learn through. But yeah, in the interest of time, I'm gonna stop right now, and I do have another appendix slide here for you to kind of, if you're interested in, read up these papers. There's a lot of other papers that came after this. This is a screenshot that I took from that paper. I'm sure there's a lot of alumni who knows about this this area. So feel free to talk to your peers, talk to your seniors. And finally, people who are going to be building AI is going to be very small, but people who are going to be using AI or building applications are going to be bigger than that subset. So I would say I would encourage you to build applications on AI and machine learning, and hopefully you can get the benefit from the links that I've shared, and wish you all the best. And yeah, so I'll stick around if you guys have any questions, and I apologize for taking the entire 1 hour to finish the session.